Alright everyone, today we're going to be talking about area, okay, and we're going to do some more complicated examples of area this week. We're going to do some area between two functions, and eventually we're going to get to some horizontal areas. So what I would like to start out is when I think of finding the area underneath a curve, I think of creating an integral where the lower bound is where we're going from, right? What value we're starting at, where we're going to end up, where we're going to, and then my integral is going to be length times width. Okay, this is what I think of when I think of my integral, okay, in finding area. So take the example y equals x squared minus 6x plus 12. We're finding the area bounded between that and the x-axis, going from x equals 3 to x equals 5. So obviously my bounds 3 to 5, that's where I'm going from, and I'm gonna end up going to. And then I usually draw in some kind of rectangle on the graph, just kind of a representative rectangle of what I want to integrate. Okay, so this rectangle, its length is this height right here, and obviously the height comes from my function y equals x squared minus 6x plus 12, and the width is an infinitesimally small value I'm going to call a very tiny change in x, or dx. And what the integral does is when we multiply this length times width, the length being your x squared minus 6x plus 12 times your width dx, that gives you the area of one rectangle, and the integral represents adding together all of the infinitesimally small rectangles going from 3 to 5. Alright, so draw it in. It's kind of trivial to draw it in these earlier ones, these rectangles, but I still recommend you do so. Also notice that since dx, this little tiny change in x, gives us our width, our y value, that height, needs to be written in terms of x. So dx needs to be written in terms of x. All right, this will, this is a pretty easy integral to take. That's x cubed over 3 minus 3x squared plus 12x. You guys know to plug in the bounds 5 and 3 and subtract them. And this is going to give you the answer 26 thirds. Okay? You can verify that on your own. You can plug it into a calculator if you need to calculate that area. Okay? So that's, honestly, we were doing that last week, but I just wanted to kind of hit it again. In example 2, I'm going to give you a couple different ways to go over this. This is, again, finding the area bounded by this line and the x-axis going from 0 to 5. Now, creating our integral from 0 to 5, we know that the integral itself is going to take these negative values, these areas below the x-axis, and count them as a negative area, and the one at the positive above the x-axis is a positive area. But we don't want that. When we say find the area, we're not looking for signed area. We're not looking for the negatives here. So what we have to do is that integral going from 0 to 3, we're going to have to take that integral separately from the second integral going from 3 to 5. And we're going to have to make this integral positive. So either plop a negative in front of it or put wrap it in an absolute value. And I'll show you a way that you can do this in your calculator in just a single step. But for now, our rectangle, again, has a width of dx, has a length of y, which is 2x minus 6. So length times width. Over here, this is also length times width. And we can go ahead and integrate both of these terms. subtract the bounds, and so on. I'm going to leave that up to you to calculate it. You should get an answer of 13. Okay? Now, alternatively, we know a transformation that's going to take this portion below the x-axis and can flip it up and can make it positive so that we can get a positive answer. So that we could do this as a single interval going straight from 0 all the way over to 5. And of course, that's an absolute value transformation. We could actually take the integral with our function being the absolute value of 2x minus 6. And in your calculator, you would plug in 0 to 5, absolute value of 2x minus 6 dx. Just be careful with your calculator. I did this earlier, and the answer it gave me, because it's using numerical methods to kind of like approximate and get a really, really, really super close answer, it didn't actually come out to 13. It came out to 12.99999 and so on. All right. I think it had 5 9s and then like an 8 7 or something like that. So be careful with that. It's still close enough to 13 that 13 is going to be your answer. But if you're using a calculator, you can just go ahead and do that as an integral using the math button and find absolute value, ABS. You can put in those absolute value bars in an integral and calculate it out. Okay? Of course, if the entire area is below, just take the integral. This is going from -1 to 4, and here's our representative rectangle. It's below the x-axis, so the integral from -1 to 4 of this x plus 1, x minus 4 dx. If you calculate it, just to absolute value it, the answer that you're going to get, your answer is going to be -125 over 6. So the area here is going to be equal to a positive 125 over 6. Okay? So be careful with those regions below the x-axis. Now, moving right along. Finding the area not bounded by an axis but bounded by a line. So here we have two functions. We've got the horizontal line y equals 3. We've got this parabola y equals 1/2 x squared plus 1. And we want to find the area. Now this is where it becomes more important to draw in that representative rectangle here. Okay? We can see that there's a little tiny horizontal change for this rectangle that's going to be our width. So we're going to call that dx. But the height or length of this rectangle is the distance between the line and the parabola, right? So how do we go ahead and find the distance between two functions? Okay, there's a simple rule that I'm going to end up using, and I want you to try and use it. That will always give you a positive answer. You're never going to have to worry about are you below the x-axis, are you above, is one function below, is the other one below. Like all of that flies out the window if you can just remember top minus bottom. Okay, this height here is going to come from the top function of 3 minus the bottom function 1/2 x squared plus 1. Please make sure you put in the functions with parentheses if you need, but top minus bottom will always give you a positive answer. The only time you have to be careful is if the top function and the bottom function intersect and switch, right? but so far there's not any examples of that happening here. Our integral is going to go from, now it's either going to go from -2 to +2, or what I'm going to do here is I'm going to use the symmetry, the fact that both functions here are symmetric about the y-axis, that this left-hand side region, if I call that region 1, and region 2 on the right, they're the same. So as an easier integral, I can go from 0 to +2 and then just double it. So just find the area of region 2 and then multiply it by 2. Why do I say that's an easier integral? Because if one of your bounds is 0, well, that's really nice to plug into a lot of these polynomial functions that we're integrating. So 0 as a bound is great when you can do it this way, all right? So using the symmetry, I can take the integral from 0 to 2, I can double it. The height is 3 minus 1/2 x squared plus 1. dx is our width, so that's length times width. Integrate means we're going to add together all of the rectangles going from 0 to 2, and then we double it to find the area. This area, you guys can go ahead and calculate it. You can simplify what's inside, make sure you distribute that negative across. Do the integration, plug in the bounds, get an answer, and then double it. You should get 16/3 for the answer to that integral. Okay. Now this idea of top minus bottom, I'm doing a simple example here where the line is on top. Here's an example where the line is on bottom. Again, not a tough integral to take if you can remember top minus bottom. We've got our rectangle, tiny change in x, dx, that gives our rectangle a little bit of width. The height is going to be the sine of x curve plus 3, and the bottom function is 1. So top minus bottom is sine of x plus 3 minus 1. We can integrate that, going from 0 to 3 pi over 2 sine of x plus, just say plus 2 at this point, dx. Go ahead and calculate that up. You will need a calculator for this one, plugging in some of these values after you integrate. It's I ended up getting 9.618, and it goes on. Right? The last one area that we're going to do today is the area between two functions. We've got y equals x. We've got y equals x squared minus 3x. Okay, and so we're looking for the area that is in between these two curves. So this whole area down here, to find the area, we need to be able to find the bounds. So one bound is over here at 0, 0. And another bound over here we can see from the graph is at 4. You can check and make sure that 4, 4 fits into both of these functions, which it does, 4, 4. Right? I'm going to draw in my representative rectangle in here. Doesn't have to look perfect. The width is dx, and the height of the rectangle, top minus bottom, y equals x is my top function, and x squared minus 3x is my bottom function. Multiply by dx, that gives me the area of the representative rectangle, and then we want to add and accumulate all of the rectangles going from 0 to 4. That's my integral. Integrate it, and you will get 32/3. All right. Try these integrals on your own. Make sure you're coming up with the same answer that I am. You can do all that little legwork. There's going to be some problems that I'll be putting out for you guys to practice on. If you have any questions, email me. Great. Thanks.